Alright, so now we're going to go back the other way, integration, but at this stage we can't integrate inverse trig. We'll look at some techniques in extension 2 later on that will allow us to do that. The integration that we're going to look at involves inverse trig. In other words, we're basically going to go the reverse of what we did yesterday. So if I have, well, this is what the standard integral looks like. They do it for linear functions. So dx on a squared minus x squared, that becomes inverse sine. Of course, it could also be inverse cos. Because if you remember, the difference in the derivatives was just one was positive, one was negative. So if you preferred to use inverse cos, you could, but it'd be the negative of inverse cos. Because the integral would have to be minus on the top to get inverse cos. So you have a choice which one you could use. And so the other standard integral then is just the a squared plus x squared one, which is inverse tan. But again, we've got to be careful with that one, with the one on a out the front. Let's have a look at this one. So it's in the form square root of a squared minus x squared. So we know it's inverse sine or inverse cos, depending on which we want. The a is 2, so it's just inverse sine of x on 2. Again, there's a squared plus x squared, but with inverse tan, we've got to remember to go 1 on 3, inverse tan x on 3. A definite one? Well, square root of 2 minus x squared, that's in the inverse sine form. So we'll have inverse sine, but we're going from 0 to 1. And you'll find those numbers popping up a lot. Root 2 when you're dealing with inverse sine. When you're dealing with inverse tan, root 3 amazingly pops up a lot. Because of course it's the exact ratios. So you might see that. So when we sub in 1, oh look, we get 1 on root 2. We happen to know what that one is. Inverse sine of 1 on root 2 is, of course, minus inverse sine of 0. So we get pi on 4. Now again, whenever we're using calculus and trig and inverse trig, radians is the measure. Because to say that was 45 minus 0, which is 45, is incorrect. I mean, pi on 4 does not, the number pi on 4 does not equal the number 45. So if we were using this to find the area under a curve or something like that, and I said, oh, well, the area is 45, well, it's not. The area is 3.14, etc., divided by 4. Vastly different answers. Okay? So we must use radians with this. We don't have a choice. Find the derivative of the inverse sine of e to the x, hence evaluate this integral. Well, if I had no idea how to find the derivative of inverse sine e to the x, you know what I'm going to say it is?
That.
Yeah. Because I figure, you know, go back the other way. Oh, what do you get? Inverse sine. I mean, it's kind of logical. That's why they're asking us. Problem is with something like this, it's one step, so it really does look like I'm cheating, and I don't know how to make it look like I'm not cheating, because I would look at that and go, oh, inverse sine. So it's the derivative over the square root of 1 minus the function squared. Ah, there you go. I mean, how do I make that look like I'm not cheating? It is one step. That is the derivative of the inverse sine of e to the x. Hence evaluate, oh, well, okay then. Therefore, if I integrate e to the x on the square root of 1 minus e to the 2x, I get inverse sine of e to the x. Now, subbing in minus log 2 to 0. So, inverse sine of e to the 0, well, e to the 0 is, of course, 1. Inverse sine of 1 is pi on 2. Inverse sine of e to the minus log 2. Right? In order for the e and the log to cancel, it needs to be e to the log, not e to the minus log. So I need to bring the 1 into the log. So it becomes the log of 2 to the power of minus 1. 2 to the power of minus 1 is, of course, a half. And so e to the log of a half is just a half. Inverse sine of a half, pi on 6. Pi on 2 minus pi on 6, pi on 3. Now, 9x squared. Our standard integral is a squared minus x squared, not a squared minus 9x squared. So how to deal with something like this? Well, I could factorise the thing causing me the problem. So if I factorise the 9 out, and now I've got minus x squared, and but the a squared becomes 4/9. The 3, I can, well, bring it out the front of the integral because we're allowed to factorise constants. So I could change that integral to be 1/3 dx on the square root of 4/9 minus x squared. So a squared is 4/9, which means a is 2/3, but remember it's x on a, so x on 2/3 with the same as 3x on 2. So put that all together, 1/3 inverse sine 3x on 2, plus, of course, a constant. All right, let's add these to our list.